Alright, I'm just going to go through the solutions of this worksheet on increasing, decreasing functions and stationary points so that you're ready for the mini quiz on that material. Number 1 says find the intervals where f of x is increasing. Alright, well we can just do this by actually looking at the graph. Sorry, I'll just get my pen. Alright then, by looking at the graph we can see that we are increasing, as we go from left to right, we are increasing for all values of x that are less than 0. And then we start decreasing between 0 and 2. So we're decreasing in between 0 and 2. We are then increasing again between 2 and 6. Oops. Positive 2 and 6. And finally we are decreasing again everywhere after 6. So for values of x greater than 6. You could also express your solution in interval notation. So you've got everything less than 0, we could say is everything from negative infinity up to 0, where 0 is not included, and of course infinities are never included. And we've also got everything from 2 to 6. So it's those two regions, and similarly down here we've got everything from 0 to 2, and everything from 6 up to positive infinity. So that's interval notation. Doesn't really matter if you have a comma or if you have a u in between them. They effectively mean the same thing, but maybe just to be consistent I'll change it to a u and move on to number 2. Now here we have to find the same kind of question. We need to find out where f is increasing or decreasing, except that we haven't been given the graph. See, this one was nice because we knew where our stationary points were, and just by looking at the x values of those stationary points we could see that we were decreasing from 0 to 2, and we were increasing from 2 to 6. However, in number 2 we don't have those graphs. So perhaps the first thing we should do then is to find out sort of where my graph is going to be horizontal. Perhaps we should use the calculator to just draw a quick sketch of the function. And so on my calculator we'll say that we've got x cubed minus 6x squared and let's draw a picture of that. Okay, I can see that I've got a cubic, but I can't see all of the action right now. So it looks like I don't really need to focus on what's happening over here, but I do need to see more of what's happening down here. So I'm going to make my x min a little bit less, and I'm going to make my y min a little bit more. So I'll bring my x min to say negative 3, and my y min I'll bring to say negative 40. And let's see if that gives me a better picture. Alright, pretty good now. And so I can see that I've got a local maximum right here. This is a place where my tangent is 0. I've got a stationary point. And right here I've got a local minimum. This is another place where my tangent is horizontal, so I've got a stationary point. So I suppose I could just use the calculator to find those max and mins. I'm going to use that, and then I'll show you how to do it with calculus. So second calculus, let's find first the maximum. And so the left bound, I'll move a little bit to the left of my minimum, my maximum, which is negative 1. A little bit to the right is positive 1, and I'm going to guess that the maximum occurs at 0, and in fact, yes it does. So on my sketch over here, I've got a maximum occurring at 0, 0. And let's find out where my second stationary point is. Right? Remember, a stationary point is any place where your tangent is a horizontal line. So let's find the minimum then. So I'll move something, my left bound, something safely to the left of my minimum would be, say, positive 3. Safely on the right is 5, and I'll make my guess 4. And in fact, it does occur at 4. My minimum occurs at 4, comma, negative 32. So just by looking at this graph, I can see that my interval of increase, I'm increasing going upwards for all x values before 0. So that's all values of x that are less than 0. And I'm also increasing for all x values that are after positive 4. Okay, so that's increase. And for decrease, I can see that I'm decreasing for all x values between 0 and 4. And of course, you could also write this in interval notation, from negative infinity to 0, and from 0 to 4. And this one, the decrease is from 0 to 4. Oops, my bad over here, sorry. This was supposed to be for all values greater than 4, up to positive infinity. Good. And I'll also show you how to do this with calculus, though. So we could have done this without the calculator. We could have taken our original function and differentiated it. We know that the derivative represents the slope. The derivative will be 3x squared minus 12x. Now we know that stationary points occur wherever your slope, or if your tangent, is horizontal. And we know that a horizontal slope means that the slope is equal to 0. So, anytime that you're looking for a stationary point, let's set the derivative equal to 0. I'll factor out my 3x, and I'm left with x minus 4. So either 3x equals 0, or x minus 4 equals 0. If 3x was equal to 0, that would mean that x is equal to 0. If x minus 4 were equal to 0, that would mean that x is equal to positive 4. And so no huge surprise, we found out that our stationary points occur when x is equal to 0 and when x is equal to 4, just like we found out using the calculator. So that duplicates our results. In order to find out whether we have a minimum or a maximum at x equals 0, one technique might be to find the second derivative of the function. If you found the second derivative, we'd have 6x minus 12. So let's find out what the value of the second derivative is when x equals 0. Okay, the second derivative is going to be 6 times 0 minus 12, which will be, negative 12, won't it? And negative 12, because that's a negative value, that means that it is concave down. And concave down means that it is a maximum. Look, whenever it is opening downwards, then that curvature shows us that this stationary point, the place where the first derivative was equal to 0, this stationary point must be a maximum. And we can do the same thing. Let's check the value of the second derivative when x is equal to 4. So we'll put in 4 into the second derivative just to find out what the curvature is like. This is assuming we did not have a graph, of course. We got 6 times 4 minus 12 equals positive 12. Because that's a positive number, that means that it is concave up in this region. And anytime that you have a stationary point where the second derivative indicates that it is concave up, then that means that we have a minimum. And so because we know the location of the maximum and the minimum, we can of course figure out that it was increasing before the max, decreasing between the max and the min, and then increasing after the min. So I'm going to show you how to do number 2 entirely without using the calculator. So let's start by differentiating the expression. And I know that stationary points occur wherever the first derivative is equal to 0. So, so there we go. Let's find out where is 6x squared plus 18x plus 6 going to equal 0. Well, I was hoping for something that would factor, but shoot, I can see that this one is not going to factor nicely. So perhaps I should find out where my stationary points are by putting this into the calculator and to say polysimilt or something. So let's turn it on and go to apps. Oh shoot, I don't have polysimilt on this calculator. Well, no worries. I'm just going to have to do it with the quadratic formula instead. You guys, I hope, will have a better method. Oh, I know how I can do it. Quickly using the calculator, I can put in a brand new function and find out where the zeros are, find out where it's equal to 0. So I've got 6x squared plus 18x plus 6. Oops, the x didn't register. 6, there we go, plus 6. And let's put this on a regular graph. There it is, and we want to find out where is it equal to 0. So second calc 0, and the left bound, let's find this one on the left first. That's negative 3. Something on the right is negative 2, and a guess, how about negative 2.5? Actually occurs when x is negative 2.62. And the other place where we have something equal to the graph equal to 0, let's see, 0, left bound, right bound, guess, and it tells us it actually occurs at negative 0.382. Now, because I know something about the shapes of cubics, I know that this cubic with a positive leading coefficient is going to look kind of like this. So if I set up my values, got negative 2.62 is going to be my first stationary point, the first place where my tangent slope is horizontal, first place where the derivative is equal to 0, and the second one is going to be right here at negative 0.382. And so looking at this diagram, it's pretty clear that we have a maximum at negative 2.62 and a minimum when x equals negative 0.382. And so our intervals of increase must be everything less than negative 2.62. So this is the increasing first. X is less than negative 2.62. And after, everything after, so everything greater than negative 0.382. And the interval of decrease will be everything that's in between those things. Oops, let's start with the smaller one. So negative 2.62 is less than x is less than negative 0.382. Everything in between those, we can see that the graph is decreasing. On to number 3. Alright, we got points A, B, and C. All three of these places we can see that their tangents are horizontal, which means that all three of these places are stationary points. But each of these stationary points is different. We can see that A is a local minimum because we are decreasing beforehand, but we are increasing afterwards. In other words, any time that your derivative is negative beforehand and then positive after, so we've gone from a negative slope to a positive slope, that must represent that we were at a minimum. B is going to be a local maximum. You can see this not only from the graph, but also look at the intervals of increase and decrease. We are increasing beforehand and then decreasing afterwards. That is to say that your slope is positive and then negative, meaning that your first derivative is positive and then your first derivative is negative. And in between, point C, this is called a horizontal point of inflection. Inflection can be spelt with a CT or with an X. I've seen it written in both ways, so let's just be aware of both spellings. And C is a horizontal point of inflection because it is a place where we were horizontal, but it is neither a maximum nor is it a minimum. We were decreasing beforehand, and then we're decreasing afterwards. So if the first derivative is negative before and the same sign, negative afterwards, well then that stationary point must be a horizontal point of inflection. This could also occur if we were increasing, so a positive first derivative, and then we got horizontal, and then we were positive again. This would be another situation where we have a horizontal point of inflection. Remember that points of inflection are places where, if you're driving a car, your steering wheel has gone from a right turn into a left turn. It's at the instant that your steering wheel is neither turning to the right nor to the left. And here we were turning to the left, and then right at this instant, oh sorry, what am I talking about? No, I'm down here, aren't I? I'm turning to the left, and right at this instant I begin turning to the right. And so that would be a horizontal point of inflection. So you can always classify stationary points by looking at the sign of the first derivative. That is to say, whether the slope or the gradient is positive or negative before and after each stationary point. If you have gone from positive, that is to say a positive derivative increasing, to a negative first derivative decreasing, then that is when you have a max. If you have gone from a negative first derivative, so we're decreasing, to a positive first derivative after the stationary point, so we check the sign of the first derivative on each side, we went from negative to positive, that signifies that we are at a local minimum. And if the sign doesn't change, like we went from negative to negative, or if we had gone from positive to positive, well then that would be a horizontal point of inflection. Okay? So it says to draw a sign diagram for the gradient of f of x for all of x. So our sign diagrams are always like number lines, and we're going to indicate the three important x values. That's negative 2, 0, and positive 3. Negative 2, 0, and positive 3. We're drawing a sign diagram, which means that we want to put pluses and minuses into each of these four intervals that have been created. It's going to, because we're looking for a sign diagram at the gradient, we need to find out whether the gradient, that is to say the first derivative, is going to be positive or negative. Well, I can see that my first derivative, my slope, is positive in this region. But then my first derivative, or my slope, I'm decreasing, it becomes negative. Then between 0 and 3, I'm still decreasing. But then after 3, I begin increasing. And so that's a positive first derivative, a positive slope. Alright, so that's a sign diagram. And we know that any time that we went from positive to negative, that must have been a max, right? Imagine what your graph is doing. And then any time that you go from a negative to a negative, that's a horizontal point of inflection. And then when we finally got to 3, we started going up again, and that made it a minimum. Okay? Let's move on to number 4. At what value of x does the quadratic function have a stationary point? Well, we know that stationary points occur when the derivative is equal to 0. That's what a stationary point means. It's code for the first derivative is equal to 0. So let's find out what the derivative of the function is. So our original function is ax squared plus bx plus c. Let's differentiate it. So the a hangs out in front, and the derivative of x squared is 2x. In the next expression, the b hangs out in front, and we know that the derivative of x, it just disappears, and then the derivative of any constant just disappears. So I'm left with this expression. And I know that this thing is equal to 0 at the stationary point. And so so it says at what value of x? So let's multiply this out. We've got a times 2 times x, or 2ax plus b is equal to 0. Let's isolate x. So 2ax equals negative b, and then I can divide both sides by 2a, and I find that x equals negative b over 2a. If that looks a little bit familiar to you, I hope it is, because imagine that this is your axis of symmetry in a quadratic, right? If you've got a quadratic function, your axis of symmetry, we remember, is x equals negative b over 2a. And of course, your axis of symmetry goes right through the value of x on your parabola, which is stationary, because you've got a horizontal tangent point. Okay? It says under what conditions is the stationary point a local maximum or a local minimum? Well, we know this, right? We know that if the a value, if the leading coefficient in a quadratic is greater than 0, then that's going to be a concave up, which means that we're going to have a minimum. However, if the value of a is less than 0, then it's concave down, and that means that we will have a maximum. Number 5. For each of the following functions, we need to find and classify the stationary points, and then we'll be able to sketch the functions with all of the important features. Okay, so I'm going to start by finding the derivative, which is 3x squared, and I know that for stationary points, my derivative is equal to 0, and this will occur when x is equal to 0. Now that's only the x-coordinate of the stationary point. If I'm actually going to draw a graph below, I'll need to find out what its corresponding y value is. What is the y value that goes with this x value? I'll just substitute it into the original function to find out. F of 0 equals 0 cubed plus 1 equals 1. Therefore, we have a stationary point at 0, 1. Now, not only am I supposed to find the stationary point, and that will be the only one, but I'm supposed to be able to classify it. Let's do this by drawing a sign diagram. My only stationary point has an x value of 0, so I only need to explore the interval before 0 and the interval after 0. Well, let's put in a test value like -1 and +1. If I test -1 into my first derivative function, I'll get 3 times -1 squared, which equals, if I do order of operations, I must do exponents first. That equals +3. I must be positive in this region. Now let's substitute in a test value on the other side of the stationary point into my remaining interval, like +1. That also equals 3, which means I'm positive over here as well. Look, the sign of the first derivative didn't change. I was rising, I was horizontal for an instant, but then I was rising again. What kind of point is this? Obviously, that stationary point is a horizontal point of inflection. It is not a maximum or a minimum. I'm now ready to graph. I have a horizontal point of inflection at 0, 1, and I know that I'm increasing before and increasing afterwards. Because it says sketch, I'm not going to worry about the accuracy of the other points. If it had said graph, then I should do a table of values and graph several other points more accurately. Let's do 5b. Alright, I'll begin by taking the first derivative. And let's set that equal to 0. Turns out I can factor out a 3. And the x squared minus 1 factors to x plus 1, x minus 1. So I've got 3 factors, the 3, the x plus 1, and the x minus 1. Now of course 3 can never equal 0, but x plus 1 could equal 0 if x was equal to -1, and x minus 1 could equal 0 if x was equal to +1. Now we need to find the corresponding y values for these values of x. Excuse me. Alright, let's substitute these values of x into the original function so we can find out what their corresponding values of y are. When I put in -1 into the original function, I'm going to do this in my head, I'm afraid, because I don't have any room, but you should get a value of 4. And when I put in +1 into the function, I'm going to get a value of 0. And so now I've got my 2 stationary points located at -1, 4, and +1, 0. Let's draw a sign diagram so I can classify these stationary points. And so I've got an x value at -1 and an x value at +1. I need to find out whether the first derivative is positive or negative in these 3 regions. I think you can actually see that of course the first derivative will be negative in between these 2 points, because how else am I going to get from here down to there? Of course I'm falling with a negative slope. But at any rate, let's substitute into the first derivative function. See what happens. So here's my first derivative function, 3x squared minus 3. I'm going to put in a test value from each of these 3 intervals into my first derivative function. So let's put in a test value of -2, 0, and 2. My test value of -2, if I substitute it in here, 3 times -2 squared, that's 3 times 4, minus 3 gives me positive at 9. So it's a positive region. Now let's put in an x value as 0. 0 squared is 0, 3 times 0 is 0, minus 3 is -3. It's negative in that interval. And lastly, when I put in +2, you'll find I get +9 again. So I can see that when I'm on the left side of my first stationary point of negative 1, 4, I am increasing. I have positive first derivative, a positive slope. I am rising. And then I hit my first stationary point, and now I'm falling. That must mean that that stationary point was a max, or a local max. And now I'm falling, and then I hit another stationary point where I'm flat, and after that stationary point I can see that my positive first derivative means I have a positive slope, and I'm rising again, which means that this was a local min at 1, 0. And so I found both stationary points, and I classified them, and I drew a sketch of my function. I think that's all I had to do in this problem. Yeah, now if I was actually supposed to show all of the important features, there's a couple of other things I would need to find, aren't there? There are no asymptotes in either of these graphs, but we do have x-intercepts. And so I should have found those x-intercepts and any y-intercepts by using the appropriate techniques. We know that to find a y-intercept, we just substitute x equals 0 into the original function. And we know that to find an x-intercept, we're going to use the zeros feature on the calculator to find out the location of that x-intercept. Last question on this worksheet was number 6. We're told that this function has got a stationary point located right here. That means that when x is 2, we have a stationary point. Stationary point means that the derivative is equal to 0. We know in this case that our derivative is going to occur. We know that our derivative is going to occur when x is 2. That's when the derivative will equal 0. Well, let's first start by finding the derivative. The derivative of x cubed is 3x squared, and the derivative of ax is a. We're done. If we set this function equal to 0 to find out the stationary points, but we remember that the stationary point occurs when x is equal to 2. And now we can solve for a. And you'll find that a is equal to negative 12. To find the value of b, we can substitute in, let's see what we got so far. Our function, we've now sort of solved the riddle slightly. We've got x cubed minus 12x plus the unknown value of b. Let's substitute in this known point on the curve, because the stationary point, while it's a place that's flat on the curve, it is a point on the curve. So we know that it satisfies this equation. Let's put in the y value and the x value, and now we'll be able to solve for b. Let's bring the 8 across, becomes a minus 8, and the negative 24 becomes a positive 24. And now you'll find that b is equal to 13. Part B, find and classify all of the stationary points. So we've now got, well, we've got the stationary point 2, negative 3. That was given to us. And it's only a cubic. We know that cubics with positive leading coefficients look like that. So we're only going to have 2 stationary points, and we've already got one of them, so there's only one other stationary point to find. Anyway, let's have a look at the first derivative, because we know that stationary points occur where the first derivative is equal to 0. 3x squared plus a, and a was negative 12, so there we go. There's our first derivative equal to 0, because that's what a stationary point is, a place where the first derivative equals 0, and I've solved for a by now. Let's factor out the 3, and look, we get a nice little difference of squares that factors to x plus 2, x minus 2. And so your stationary points occur at x equals negative 2 and at x equals positive 2. Now x equals positive 2, we already knew that this corresponding y value was negative 3, but we are going to need to substitute the negative 2 back into the original function to find out what we get. Okay, so the y value is going to be negative 2 cubed minus 12 times negative 2 plus b, and we remember that b was 13, and that gives you negative 8 plus 24, that's 29. Okay, so we've got then the coordinates 2, negative 3, and negative 2, 29. And, well, something feels funny here. I was expecting this one to be the minimum, And, oh, I see. Yes, the negative 2 is the one on the left, isn't it? Because that's the first value of x. So that's my negative 2, 29. Look, it goes all the way up to 29 as the max. And then it comes all the way down. By the time we reach positive 2, it's gone all the way down to negative 3. And that is, of course, a minimum. And there we go. We have now classified. You can see if we had had a sign diagram, we'd have had critical values at negative 2 and positive 2. And obviously, when we are before negative 2, we can see that our first derivative value for any test value, say negative 3, if you substituted it into the first derivative, you'd find that your first derivative is positive. If we substituted in a test value between negative 2 and positive 2 into the first derivative, like 0, you'd find that your first derivative is negative, so we're decreasing, a falling slope. And if you substituted in a value bigger than 2, like 3, into the first derivative, your first derivative would be a positive number, indicating that we are increasing. So you can see we are increasing, we are 0 at the stationary point, we are decreasing, we are flat at the stationary point, we are increasing. Anytime that we go from positive to negative, that must be a max. Anytime we go from negative to positive, that must be a min. Okay? I hope you understand now the concept of increasing and decreasing intervals and the stationary points, which indicate the places between which we have intervals of increase and decrease. Stationary points, of course, are places where our tangent is horizontal, and so we are neither increasing nor decreasing at those points. We are simply increasing or decreasing before or after, or in between pairs of those stationary points. Alright, good luck. We will do a little bit of review on this material right before we write the mini-quiz on Friday, March 7. That's probably tomorrow for most of you listening to this video. Okay, best of luck.